Okay, so last time we started talking about the quotient topology. We defined what a quotient map is. So if X and Y are topological spaces, then a quotient map is a surjective map with the following property. A subset U of Y is open in Y if and only if its inverse image is open in X. So this is clearly stronger than continuous. This says that those subsets of Y, I can determine if they're open by looking at their inverse image. We proved that if P is a continuous surjective map, which happens to be open, then P is a quotient map. But the converse is not true, and we gave a counterexample of a quotient map which is not open. Then if we have a space X, a set A together with a surjective map from X to A, we can define a topology on A called the quotient topology that makes P a quotient map, right? And this is a mathematically precise way of formalizing what it means to identify points in a topological space, or to glue topological spaces to obtain a new one, right? To make certain identifications and obtain a new topological space. That's how we use the quotient topology in practice. So if there's a definition, if X is a topological space and X tilde is a partition of X into disjoint subsets whose union is X, then I can give a quotient topology to X tilde induced by the map that sends, by the surjective map that sends a point to the subset containing that point. And that's called, if I equip X tilde with the quotient topology induced by this map, which is called a projection map, is called, we say X tilde is a quotient space of X, right? And how does this arise in practice? Well, we obtain, given a topological space X, we can obtain a set X tilde by defining an equivalence relation on X, right? And then X tilde would be the equivalence classes with respect to that equivalence relation. So a point in X tilde becomes a subset of X. That subset might be a singleton, or it might be a bunch of points. But these are the new points in X tilde. And there's a topology induced by X on this set of points. Does that make sense? So is it clear how this formalizes the idea of gluing topological spaces? If you have two disjoint topological spaces, and let's say I want to glue them at a point, then what do? I take the disjoint union of those two topological spaces and I declare an equivalence relation that says that my two selected points on each space are the same, right? Are related. And then when I take the quotient, what I'm doing is I'm putting a topology on the set obtained by identifying those 2 points. That's why I'm saying that this formalizes the idea of gluing, or it can be used to describe what it means to glue two topological spaces or make certain identifications on a single topological space. Okay? Let's see. So, oh, the book uses this X instead of calling these partitions of X X tilde. The book uses this notation X star, but I prefer X tilde. Anyway, we gave examples, right? For example, if X is the unit disk in the plane, then I can describe an equivalence relation on X that identifies all the points in the boundary to a single point. And the points inside the disk, which are not in the boundary, they just have their own equivalence class, each of those. So if I take this equivalence relation, I get and I put the quotient topology on the set X tilde of equivalence classes, I get a space which is homeomorphic to the two sphere inside three-dimensional Euclidean space, right? And it's intuitively clear that if you collapse the boundary to a point, you get a sphere. Is that clear to everyone, that if you collapse that boundary circle to a point, meaning you make it a single point, you identify all of those at a single point, you get something that looks like a sphere, at least intuitively? Is that clear? Okay, good. And you can prove it formally, right? You can construct a homeomorphism explicitly. And this was a picture of the open sets, right? So this U here, this collar U, can be thought of as an open set around the boundary circle, right? Containing the boundary circle. And that open set in this identification goes to a little disk around the point, which represents the class of the boundary circle after making the identifications. Okay. And there's an easier example. Of course, you can consider the interval, and you can glue or identify. So the interval you consider with the subspace topology. Then you consider the set obtained by gluing the endpoints. And then there's a topology on this set called the quotient topology. And the resulting space, X tilde, after making those identifications and giving it the quotient topology, is homeomorphic to the circle. Any questions so far about the quotient topology? Okay, so this is a theorem I wanted to discuss today. So, yeah. So suppose P is a quotient map. Suppose X and Y are topological spaces, and P is a quotient map. And let Z be another topological space, and G be a map that is constant on each of the inverse images P inverse of Y for Y any point in capital Y, in big Y, okay? So I think of these, sometimes these sets are called the fibers of Y along the map P, right? It's just the inverse image of Y, everything that gets mapped to the point Y, everything that's on top of Y, you can think of, if we think of our map in this way, right? So suppose G is constant on all of those fibers over Y. So you have Y, you look at the inverse image of Y, that's a bunch of points in X. Suppose G is a function that takes all of these points on top of X, on the inverse image of Y, to takes each of these to a single point here in Z, okay? Let's suppose G is constant. Then G induces a map F from Y to Z, a map downstairs here from Y to Z, such that the composition of P and F equals G. And we have that the map F is continuous if and only if G is continuous. So this here is called the diagram. It's just a way of picturing spaces and maps between them. And this condition here, the fact that G equals the composition of P and F, we also say, if this holds, we say this diagram commutes. Sometimes write it in this way, and a curved arrow in this way. It commutes because going from here to Z, following that composition, is the same as going from X to Z using this other map, right? So this is just a picture to describe this. This composition equals this map. Okay. Good. So yeah. Let's see. So this is fairly straightforward, but it's important. So we know that by assumption, for all y in capital Y, G of P inverse image of Y consists of a single point, right? By assumption, because I'm assuming G is constant on these sets. So we define f of Y to be exactly that point over here. So if I have Y here, where do I want to define f, right? My claim is that given the assumptions, there exists an induced map f. So given Y here, where do I send it? Well, I look at the inverse image of Y here, right? And I know G sends all those points to the same point in Z, right? So I send Y to that point in Z, which I'm going to call Fy, right? So we have a map from Y to Z. And by definition, it satisfies the following, right? That if I start with an X and I apply P, then F of Px is exactly G of X, right? Because X would be in P inverse P of X, right? And if F is continuous, then G is continuous, right? So I wanted to show that first, there's an induced map F, and second, that the map F is continuous if and only if G is continuous. So first, I'm claiming that if F is continuous, then G is continuous. And that follows from the fact that the composition of continuous functions is again continuous. P is a quotient map, so in particular is continuous. So if F is continuous, then G is continuous, because we have that G equals a composition of F and P by construction. That's exactly this condition here, right? And conversely, now I want to argue that if G is continuous, then the induced map F is continuous as well. And there I'm going to use the fact that P is a quotient map. So suppose G is continuous. Suppose this G is continuous. So given an open set V in Z, the inverse image of V is open in X, by the continuity of G. But note that the inverse image of V is exactly, again, by the way I've constructed F, the inverse image of F applied to V, and then taking the inverse image along P. This follows again because G is a composition of F and P. Now, since P is a quotient map, I have that if this is open, then this set is open, right? By the definition of quotient maps. So I'm saying that this is open because it's the inverse image of an open set along a continuous map. So since P is a quotient map, it follows that F inverse of V is open. And that implies, since V was arbitrary, that implies that F is continuous. Okay? So it's kind of like a little bit of abstract nonsense, right? Manipulating these conditions and so on. And we get that if P is a quotient map and G is a continuous map from X to Z, then there's an induced continuous map from X to Z. Okay. Any questions? So a corollary of this statement is the following. So suppose G is a surjective continuous map from X to Y. And now we consider the set X tilde consisting of these subsets. The inverse images of Z, where Z runs through all points of big Z. Okay? So this collection of subsets is a partition of X, right? Its union is X because G is surjective by assumption. Right? So if I run through all points in Z and I take the inverse images along G, I get a bunch of sets for each point in Z, partitioning this X. This is like X, right? Is that clear? Okay, so I can give the quotient topology to this X tilde induced by the surjective map that sends a point X to the following subset containing it. So you take X, you apply G of X, that's a point in Z, and then you take the inverse image. That's a bunch of points which contains X, right? X is contained here. So there's a surjective map, there's a topological space, there's a set. So I can put the quotient topology here. So we have that G induces a bijective continuous map F from X tilde to Z, which is a homeomorphism if and only if G is a quotient map. So if G happens to be a quotient map, this bijective continuous map is a homeomorphism, and this will use the fact that we stated at the beginning of the class. And moreover, we have that if Z is Hausdorff, then X tilde is Hausdorff as well.
I have a question about this F map.
This F map, This will follow from the above claim, the existence. Yeah, but yeah.
I was just gonna ask, like, this is okay. Yes. So this is a map that's like taking the representatives to like the actual elements, right?
Um, I don't understand. Are you talking about this?
So if X tilde is like a set of basically equivalence classes, right? Because you've partitioned your space X, and you've partitioned it in the way of like inverse images of little z's.
Yeah.
I'm just saying this map F is like the one that takes these equivalent classes in X tilde to the representatives in Z.
Uh, I mean, to a specific representative, not quite, because I mean, if you have two representatives, then that would not be well defined, right?
You
Because that.
don't have like multiple, I mean, like
So
you just
let's.
have classes, and I'm just saying like the representative you pick gets mapped to, like
Yeah.
it needs to go exactly to that
Yeah. So
element.
let's. Yeah. Yeah. I mean, your idea is correct, but let's say it correctly. So how is F induced by the previous statement? Do you remember? First, G is a map that is constant along the inverse images of P. So if you have, so let's say, so if you have, maybe I'm going to use alpha. You have alpha in X tilde. What is P inverse image of alpha in X? What is that? So what, look at what P is. P takes a point X to the set, to this set containing X, right? So, yeah, so if you have X tilde consists precisely of the inverse images of Z, where Z runs through all points of capital Z, right? So, right. So what would, so if you have, let's say, this becomes a point. Now, this set becomes a point in X tilde, right? So what would, I'm using, I think I'm using, this is bad notation. So I should have said, why am I using bad notation? Oh, G inverse, sorry. Yeah, G inverse of Z. These are the points in X tilde, right? All these subsets are points in X tilde. So what is this? P inverse of this point. This should be a collection of points in X, right? So can anyone describe what these points are? This is a collection of points in X, such that what? Such that they are exactly contained in that fiber of Z, right? In that inverse image of Z.
I think I'm just asking, like, if you apply F to that, like G inverse of Z, you're supposed to be spitting out just Z, little Z.
Yeah, exactly.
Yeah, that's all I'm asking. That like
Yeah, oh, okay.
whatever the representative was, little Z.
I mean, yeah, exactly. Because what's F on that set on that point, right? It's just G applied to the inverse image of that, right? But G of G inverse of Z would be Z, right? Did you follow that? How do you define F in general? You look at the inverse image. How do you define F? You look at the inverse image of G, right? Inside here, and then, as we said here, you define F to be exactly G applied to that inverse image of P, right? So in our case, we will have exactly Z, as you said, right? Okay, so let's show that. So this induced map, in this case, F, is a homeomorphism if and only if G is a quotient map. So first, as we just said, by the previous theorem, G induces a continuous map F, assuming G is continuous, right? It induces a continuous map F. And F is clearly bijective in this case, right? The points here are exactly given by points in Z. By definition of X tilde, right? Are uniquely given by points in Z, right? So F is clearly bijective. By the previous theorem, is continuous if G is continuous. And as we stated at the beginning of this class, first, there's an if and only if. So let's show that if F is a homeomorphism, then G is a quotient map. So if F is a homeomorphism, then G is a composition of two quotient maps, because homeomorphisms are quotient maps. And composition of quotient maps are again quotient maps, so it follows that G is a quotient map. And conversely, suppose G is a quotient map, let's show that F is a homeomorphism. So if G is a quotient map, by the previous theorem, F is also a quotient map. But at the beginning of the class today, we stated that bijective quotient map is a homeomorphism. You'll show this in your homework, or you will prove something in your homework from which this follows immediately. So this implies that F is homeomorphism. So so that's a corollary of this theorem. So let's stare a little bit at this theorem again. What is this theorem saying? Basically says that a continuous map, if you have a quotient map from X to Y, and you have a continuous map defined with domain X, then that continuous map descends to a continuous map from the range Y to Z. In other words, continuous maps descend along quotient maps to obtain continuous maps. Does this make sense more conceptually? When I say descends, I mean this picture here. You start with a map here, then there's an induced continuous map down here, assuming this is a quotient map. That's what you have to grasp from this theorem. That if you have a map upstairs, then it descends to a map downstairs with the same target or range, Z. And this uses the fact that P is a quotient map. Questions about this statement?
How does this relate to that comment you made about like having a like coarsest like topology?
So the point is that this right here, this is the minimal, like this is the minimal amount of data you need in this space X tilde. The topology here is the topology with the smallest number of open sets, the coarsest topology, so that this condition is satisfied. That a map like that descends to a map like that. That's the idea. Okay, that's how the quotient topology was defined with this picture in mind. You have a continuous map like that, and then you have a surjective map like that, right? Then what's the smallest topology I can put here in order to obtain a map, a continuous map downstairs? And that's exactly the quotient topology. See? Okay, so let me now argue that if Z is Hausdorff, then this Z tilde, this X tilde is Hausdorff. I did not wrote that, but that should be easy, right? Because if, let me do it. So if Z is Hausdorff, let me copy the picture here. Oops. We have this picture, right? This is G, and this is the map induced. We usually use dotted lines for the induced map. So I claim that if Z is Hausdorff, then this X tilde is Hausdorff. So how does this follow? So suppose Z is Hausdorff, and now suppose we have 2 points P, 2 distinct points P and Q inside X tilde. So, this is really bad notation, of course. So let's say A and B points in X tilde. So I want to show that I can find open sets around A and around B such that they are disjoint, assuming I have that property for Z. So what do? I look at the images of these points in Z. And they are distinct points because in this case, F is a bijection, right? So they are distinct points. So that means I can find U, open sets U and V, open in Z, around them such that they're disjoint, right? And
wait, how did you know that F was a bijection?
In this particular case, F is a bijection, right?
I thought like A and B were separate.
Sorry?
I thought A and B were separate. I didn't think you were assuming things in A and then trying to show things in B. I thought the statement in B is just if
Oh,
Z is
no.
Hausdorff.
The statement in B, is regarding to this setting. So X tilde is this particular set, right? So
Yes.
when X tilde is this particular set, then F is a bijection, right? Because X tilde is, the points in X tilde are uniquely given by these guys, right? These sets. So there's a bijection from X tilde to Z, sending this set to Z, right? That's actually a comment you said at the beginning. And this is clearly a bijection by the way I'm defining here my sets, right?
It's fine. You can continue.
So yeah, so this part B is part of this corollary of this setting. So if I have this setting here, then F is a bijection. And then since F is a bijection, these are distinct, A and B. So I can find open sets around them. And then F inverse of U and F inverse of B will be disjoint open neighborhoods because F is continuous. Containing A and B respectively. So I can separate this A and B. So it follows that X tilde is Hausdorff as well. Okay. Any questions regarding the quotient topology?
I guess I have a question. If
Yeah.
we start a metric space and take a quotient topology, do we get a metric downstairs in the quotient topology?
That's a good question. Let me think. I think that's not the case. I don't have a counterexample off the top of my head, but that could be a good exercise.
Okay.
Yeah, there's a lot of, I mean, many things go wrong, as you'll see in your current homework. For example, the quotient topology does not even behave good with subspaces. There's an exercise in the homework making this precise. Also, Hausdorffness is lost, right? I mean, this is a sufficient condition in a very particular space, in a particular case, for this quotient space to be Hausdorff. But in general, I mean, in general, if X is Hausdorff, and if X is Hausdorff, and I put the quotient topology on some set, that will not be Hausdorff. Okay, so many of these things don't pass to the quotient space. Many, and products as well. It's not the quotient topology is not quite compatible with products. You can make precise what this means. So, yeah, many of these things fail in the quotient topology. Yeah.
I have a question about Hausdorffness.
Yeah.
So I remember we defined it in this way where if you have any 2 points, you can get open sets around them that are disjoint. And then I think we said if something is Hausdorff, then the only sets that are open and closed are the whole thing and the empty set.
No. That's if something is wait,
Connected.
say that again.
Connected.
Yeah.
Connected.
The only sets that are both open and closed are the empty set and the
Thank you.
whole thing itself. Yeah. There's another, you might have something in mind. There's another equivalent condition for Hausdorffness, which is very useful in these arguments, which is regarding the diagonal in the product of a space with itself. Can anyone recall that equivalent formulation of Hausdorff-ness? A space is Hausdorff if and only if what?
Isn't it if the diagonal is closed?
The what?
The diagonal, like if
Yeah.
X is Hausdorff, then the diagonal in X cross X is closed.
Yeah. It's equivalent to being Hausdorff, actually.
Right.
You can just think about what the diagonal in X cross X is closed means, right? It precisely means, I mean, let me just do it here. So X is Hausdorff. X is a space if and only if diagonal, which I'm denoting by delta, inside X cross X is closed, right? What does that mean? That is it clear what the diagonal is? It's all points of the form X times X, right? Where X is in X. That's the diagonal, right? So what was this a homework problem?
Yes.
Okay, but it's a clear, like intuitively, can you just very quickly understand why? Because what does it mean that the diagonal is closed? It means that the complement is open. But what's the complement? It's all pairs of distinct points, right? So what does it mean that it's open? That there exists an open set around any point in the complement that is inside the complement, right? But you can take this open set to be a basis element in the product topology, which is a product of open sets, U and V. And the fact that this lies inside the complement of the diagonal means exactly that U and V are disjoint. Because the complement of the diagonal consists of all pairs of distinct points. Done, right? So it's just a quick reformulation of what it means to be Hausdorff. Okay? So I think this is all for the quotient topology. Let me quickly say where we are moving to in the next 3 minutes. So we're going to discuss connected spaces and compact spaces in the next chapter. Okay, you've probably seen these assumptions or these conditions being used in some calculus statements, right? Like the intermediate value theorem, for example, uses the fact that intervals are connected. The maximum value theorem, which says that a continuous map on a closed interval, there exists an element such that the maximum is attained. This is really using the compactness of closed intervals. So you've seen connectedness and compactness used in calculus, but it's a topological notion, and we're going to describe it topologically. So connectedness, we're going to start with connectedness. You already saw a definition in one of your homework sets. There are a few equivalent formulations. So let me define, so suppose X is a topological space. So a separation of X is just a pair UV of disjoint non-empty open subsets of X whose union is X. That's a separation. And we say the space X is connected if there is no separation. If there are no disjoint open sets, non-empty, such that their union is the whole space. I claim that's equivalent to the definition that we gave in the homework. Namely, X is connected in this sense above, that there is no separation, if and only if the only subsets of X that are both open or closed are the empty set and X itself. Can someone explain the proof of this claim for me? Suppose, yeah, so If you have a separation, what does this mean?
Means you have at least two open sets
Right?
that are complements of each other in X,
Yeah,
neither of which is empty.
exactly. The disjoint property means that they're a complement to each other, right? That's the same as A and B being disjoint, right? So since they're complement to each other, that means that both A and B are both open and closed, right? And all of this implications I used right now are if and only ifs, actually, right? So this is exactly reformulation of the fact. This definition of connectedness is a reformulation of the fact that the only subsets of X that are both open and closed are the empty set and X. Okay? Okay, so on Wednesday, we're going to prove a few lemmas about connected spaces, and then we're going to describe how to construct connected spaces, new connected spaces out of collections of connected spaces, right? So let me just say what we're going to prove. So we're going to prove that the union of a collection of connected subspaces of a topological space X that have a point in common is again connected. We're going to prove that if A is a connected subspace of X and B is a subset or a subspace which contains at A, but it's contained in the closure of A, then B has to be connected as well. We're going to prove that the image of a connected space under a continuous map is again connected, and we will prove that a finite Cartesian product of connected spaces is again connected. So all of these statements give us ways of constructing connected spaces out of other connected spaces, right? Okay, so we will continue with this on Wednesday. Any questions?